And he will talk about initial algebras for topologically enriched multi-sorted algebraic theories. Thank you very much. You can start.
Great. So thank you to the organizers. So I'll just dive right in with some background to start. Oh, 1 second. There we go. Okay, just to introduce the topic and give some background. So basically, classical multi-sorted algebraic, or I will actually call them equational theories, and their initial or free algebras have been fundamental in mathematics and computer science. For example, in studying algebraic specification and algebraic data types, computational effects, and even recently algebraic databases and data integration. Now, these classical theories are set enriched in the sense that their algebras are multi-sorted sets or families of sets that are equipped with finitary operations that must satisfy certain equations. There's a well-known explicit and constructive and in some sense inductive description of their free algebras in terms of what we can loosely call term algebras. And I will review that shortly as well. Okay, so in this talk, given a symmetric monoidal category V that is topological over set, which I'll explain shortly, I'll define a notion of V-enriched multi-sorted equational theory that recaptures the classical notion when V happens to be set. So the algebras for these will be multi-sorted objects of V or families of objects of V, equipped with what I'll call V parameterized finitary operations that must satisfy certain kinds of equations as well. And to relate these to the classical theories, so every V-enriched multi-sorted equational theory T will have an underlying classical theory of vertical bars T. And crucially, using the fact that V is topological over set, it will follow, or it can be established that free T algebras are basically suitable liftings of free algebras for the underlying classical theory. So I'll give some examples of these, and I'll explain their connection to this basically established theory of enriched algebraic theories and enriched monads relative to a subcategory of arities when V happens to be symmetric monoidal closed. Okay, so I'll start by reviewing the classical theories, just to kind of ground everything that I talk about later on. So we'll fix a set S of sorts. Then a classical S-sorted signature is a set of operation symbols sigma that assigns to each operation symbol little sigma a finite tuple S1 through Sn of input sorts and an output sort S. And we can visually represent all of that data in this way. Okay, so then given a context V bar like this of S sorted variables, so each variable has a specified sort. For each sort S, we can define the set of sigma terms of sort S in context V bar, denoted like this in a standard way in logic. Okay. And that allows us to then talk about equations. So a sigma equation in context, which is denoted like this, is a context V bar and a pair of sigma terms, S and T, of the same sort in that context. And then finally, we can define what equational theories are. So a classical S-sorted equational theory is a pair T of a classical S-sorted signature sigma and a set E of sigma equations in context. And then we can interpret these theories, of course. So a sigma algebra A is an S-sorted carrier set. So it's an object of the product or power category set to the S that's equipped with, for each operation symbol little sigma, a function sigma super A of this kind, where sigma has these input sorts S1 to Sn and output sort S. And then given a context V bar, we can interpret each sigma term of sort S in context V bar in the sigma algebra A as a function like this, where T1 through Tm are the sorts of the variables in the context, and S is the sort of the term. Okay. And then we can say that a sigma algebra A satisfies a sigma equation in context like this if the interpretations of the two terms in A are equal. And then finally, given a classical theory T, a T algebra is just a sigma algebra that satisfies each equation in T, or in E, the set of equations. So we get a category sigma algebras and their morphisms, which we can define in a standard way, and a forgetful functor U sigma from sigma alg to set to the S that sends each sigma algebra to each sigma algebra to its carrier S-sorted set. And given a theory T, we get a full subcategory T alg of sigma alg, and we can restrict the forgetful functor U sigma to get UT from T alg to set to the S. Okay, so now we can review Fourier algebras for these theories, which have a well-known description. So that's what I just said there. So we'll start with first describing the Fourier algebras for a signature, because the Fourier algebras for theory are basically built from the former. So given a signature sigma, we can describe its Fourier algebras. So given an S-sorted set X with component sets X sub S, we first define kind of an augmented signature, sigma sub X, that we obtain from sigma by adjoining for each sort S and each element X in the set X sub S, a new constant symbol, which we can write as C sub X of that sort. So basically, we're joining new constants for all of the elements in the component sets of capital X here. Then we can consider the S-sorted set, denoted like this, of ground sigma sub X terms. So all the terms that we can form over this signature in the empty context using no variables. This carries the structure of the free sigma algebra F sigma X on X, which basically interprets the operation symbol syntactically. So given an operation symbol little sigma, we just interpret it as the function sending an appropriate n-tuple of terms to the term that you get by applying sigma to that n-tuple. Okay, so those are free sigma algebras. Now if you have a theory T over sigma, then to construct the free T algebra FTX on an S-sorted set X, you consider what's called the smallest sigma congruence, tilde E, on this free sigma algebra that is generated by E. So basically it's kind of the smallest sort of component-wise equivalence relation that respects the operation symbols of sigma and sort of equates all the elements that must be equated by the equations, roughly speaking. So then a quotient sigma algebra, F sigma X modulo this sigma congruence is the free T algebra on X. So basically we can kind of refer to each of these constructions, F sigma X and F sigma X mod tilde E, as a kind of term algebra construction, very loosely speaking. Okay, so now I will move on to enrichment of these classical theories. So the kind of objective of this, work was to develop an enriched notion of multi-sorted equational theory, for which the free algebras can still be described very explicitly and constructively using a kind of enhanced or augmented term algebra construction. So to achieve that, we considered a symmetric monodal category V, such that Hamming out of the unit object I from V to set, which is of course a functor, is strict monodal with respect to the Cartesian monodal structure on set and topological. Now, I won't give the full definition of the latter concept, but basically it means that this functor is faithful, and it's a very strong kind of bifibration. So we have lots of examples of this setting. We have set itself, but less trivially, we have lots of categories of topological and measurable spaces. We have the categories of models of so-called relational Horn theories without equality, which include, among many, many other examples, the examples of preordered sets and extended pseudometric spaces where you allow infinite distance. We have the categories of quasi-spaces, also known as concrete sheaves on concrete sites, which have recently kind of been studied quite a bit in computer science generally. These include things like diffeological spaces, quasi-Borel spaces, phrenological sets, abstract synthetic complexes, and so on, and lots of more examples in this class. And many of the categories studied in monadotopology as well, and also many others not in this list of items. Okay, so I will now describe the enrichment of the classical theories given such a V. So we'll fix a set S of sorts as before. So we'll start with the signatures. So a V enriched S sorted signature is a set of operation symbols sigma that assigns to each operation symbol, little sigma, a finite tuple of input sorts as before, output sort as before, and the new ingredient is a parameter object, P of V. And given these data, we said that sigma has type like this. So the input sorts, output sort, and the parameter object. So now a sigma algebra A is an S sorted carrier object of V. So it's an S sorted family of objects of V, or an object of V to the power S, that equips, or that is equipped with, for each operation symbol little sigma of this type as above, a morphism of V like this. So sigma super A from P tensor, the product of the relevant sort objects to A sub S. So the parameter is acting on this product of input sorts. And that is what kind of gives the enrichment, loosely speaking. So we get a category sigma alg of these algebras and their morphisms, which we can again define in a natural standard way. And a forgettable functor U sigma landing in V to the S that just forgets all the algebraic structure. Okay, so those are the signatures. We can now talk about the theories. So to do that, first we have to talk about underlying classical signatures. So every V enriched S sorted signature as before, sigma, has an underlying classical signature, vertical bar sigma. So how this works is that for each operation symbol little sigma in big sigma of type S bar SP, and each element little p in the underlying set of the parameter object P, this underlying signature vertical bar sigma has an operation symbol sigma sub P with the same input sorts and output sort. So vertical bar sigma consists of exactly these operation symbols sigma sub P for all sigma with parameter P. And then because this is a classical signature, of course, we can consider vertical bar sigma equations in context, or sort of equations over this signature. And also every sigma algebra A has an underlying algebra for the underlying signatures. This can be constructed in a very natural canonical way. And this assignment extends to a functor from sigma algebras to vertical bar sigma algebras. Okay, so now we can define the V enriched, or a V enriched S sorted equational theory to be a pair T of a V enriched S sorted signature sigma and a set E of vertical bar sigma equations in context. So, or a set of equations over the underlying classical signature. So if we define vertical bars T to be the pair vertical bar sigma with E, this is a classical S-sorted equational theory that we can call the underlying classical theory. And the T algebra is just a sigma algebra A, whose underlying algebra for the underlying classical signature is a an algebra for the underlying classical theory. So it satisfies every equation in E. Okay, so those are the definitions. Oh, almost. And then we have a full subcategory T-alg of sigma alg, and we get a forgetful functor ut from T-alg to v to the power s. Okay, so now I can give some examples. So this first slide will have kind of examples that are just based on classical theories. I'll get to some more properly enriched examples on the next slide. So every classical multi-sorted equational theory T determines or induces a V-enriched multi-sorted equational theory that we can just call T star, for which a T star algebra can be described as a T algebra sort of in V. So for example, there are V-enriched single-sorted, so where S is just a singleton set of sorts, equational theories whose algebras are internal semigroups or monoids or groups in V or commutative ring objects in V, and lots of other examples in this vein. When V is Cartesian monoidal, we can define a V-enriched n-sorted or natural number sorted equational theory whose algebras are symmetric or not V-based operads. When again V is Cartesian monoidal, given a fixed or given any set O, we can define a V-enriched O times O sorted equational theory whose algebras are V categories with this object set O. And for each small ordinary category A, there's a V-enriched ob of A, or objects of A sorted equational theory whose algebras are the functors from A to V. Okay, so now for some more properly enriched examples that are not of the flavor from the previous slide. So we can just let V be top, or really any suitable category of topological spaces. Then there is a top-enriched single-sorted equational theory whose algebras can be described as sort of strict or coherent H spaces, by which I personally mean internal monoids in top, whose product operations are only associative and unital up to specified homotopies. More generally, if you take any classical S-sorted equational theory T, you can define a top-enriched S-sorted equational theory T sub H that I'm choosing to call the homotopy weakening of T, whose algebras may be described as the T algebras in top that only satisfy the equations of T up to, again, specified homotopies. Okay, now if V is symmetric nodal closed, we can consider a small V category A, and we can define a V-enriched ob A sorted equational theory whose algebras are precisely the V functors or the enriched functors from this V category A to V regarded as a V category. And for a final example, if we're in a context where we have a relational horn theory T without equality, then a certain subclass of the relational algebraic theories of this paper here, which is called monads on categories of relational structures, these can be described as T-mod enriched single-sorted equational theories, where T-mod is the category of models of T. And these relational algebraic theories, they generalize, for example, the quantitative algebraic theories introduced in this paper here. Okay, so now I'll talk about the free algebras for these theories and how we can construct them. So first, if we have a V-enriched theory T and its underlying classical theory vertical bars T, the functor that sends a sigma algebra to its underlying vertical bar sigma algebra restricts to T-alg. So every T-algebra has an underlying algebra for the underlying theory or the underlying classical theory. And so what I have proved first is that the forgetful functor U super T from T-alg to V to the S has a left adjoint F super T, and the resulting adjunction is a lifting or a strict lifting of the adjunction for the underlying classical theory vertical bars T. So in particular, that means that this diagram here commutes strictly. So we have here on the left, sort of the extension of vertical bars from V to set to V to the S to set to the S. We have F super T on top. So the left adjoint for T algebras. We have the left adjoint for vertical bar T algebras on the bottom. And we have here the aforementioned functor from T alg to vertical bars T alg. So just to unpack this a bit more, what this means is that for each object X of V to the S, the free T algebra, F super Tx on X, it lies over the free algebra for the underlying classical theory on the underlying S-sorted set vertical bars X. So also, the free T algebra on X is, in a certain sense, completely determined by its carrier object of V to the S. And this equips the carrier object of the free algebra on the underlying S-sorted set with an appropriate structure of V. So for example, an appropriate topology. So basically what this is saying, loosely speaking, is that the free T algebra on X can be described using a term algebra construction with respect to the underlying classical theory, augmented with an appropriate structure from V. So like an appropriate topology or something else like that. So using the above theorem, we can therefore provide an explicit description of the V structure that I mentioned here, and therefore of the free T algebra on X. And when V happens to be Cartesian closed, this explicit description becomes even more constructive and inductive. And this is often the case. So most of the examples I mentioned are Cartesian closed. Well, yeah, so most are, but not all. And the details, which are too long to go into now, unfortunately, will be in the upcoming preprint, which should be out shortly. And just to kind of relate this to some earlier work as well, when T is single sorted and each parameter object is trivial, so is just the unit object of V, we recover previously established descriptions of free T algebras in certain specific examples of V, including those in these papers by Porst and Battenfeld. Okay, so to conclude, or almost conclude, so I'll now just discuss the connection between what I've talked about so far and a more well-established theory of enriched algebraic theories and enriched monads. So given an arbitrary symmetric monodal closed category V and what's called a subcategory of arities J in a V category C, that's just a full sub V category that is dense in the enriched sense. There is now an established theory of enriched algebraic J theories and J airy or J nervous V monads on C. That is basically developed in these papers by myself and Lucician Wright. So in the current setting of this talk, we will now suppose that V is symmetric monodal closed. Then we can take our V category C to be V to the power S, and we can construct a certain subcategory of arities, which I write as N sub S, whose objects are those S-sorted objects J of V, where each component is a finite copower of the unit object I, where all but finitely many are 0. Okay, so we have this subcategory of arities N sub S, and then we can talk about sort of enriched algebraic theories and enriched monads that are defined relative to this subcategory of arities in a certain sense. So more precisely, an N sub S theory is a V category T with an identity on objects V functor tau from N sub S op to T that satisfies a certain nerve condition. And a V monad T on the V category V to the S is called N sub S nervous or N sub S airy if it satisfies a certain, again, nerve condition. Okay, so the point is that, so in the context of this talk where V is a symmetric, monoidal, and now closed topological category over set, there is a correspondence between V-enriched assorted equational theories that I've been talking about and these N sub S enriched algebraic theories and these N sub S nervous enriched or V monads on V to the S. And this correspondence respects semantics in a suitable sense. Okay, so I will now just wrap up. I think that's, yeah, 5 minutes left. Okay, so classical or set enriched multi-sorted equational theories and their free algebras have played important roles in mathematics and computer science. Given a symmetric category V, that is to topological over set, I've defined a notion of V-enriched multi-sorted equational theory that recovers the classical notion when V is the specific example of set. Now, because V is topological over set, so this assumption is crucially used to get what I'll say next. Free algebras for these V-enriched theories can be explicitly obtained as suitable liftings or kind of augmentations of free algebras of their underlying classical counterparts, which, as we've seen, are can be obtained as kind of term algebras, loosely speaking. And when V is symmetric, closed, these V-enriched multi-sorted equational theories correspond to V-enriched algebraic theories and V-enriched monads for certain specific subcategory of areas. So in the future, I'm hoping to explore the potential applications of these V-enriched theories to certain topics in, say, computer science and the theory of databases. So that is it. Thank you for listening. And yeah, the preprint will be online quite soon, so watch out for that.
Thank you very much for your talk. Are there any questions either here or online? Okay, if there is something online, just please speak up. Okay, then maybe I will ask one. So could you do a similar thing with, let's say, partial theories and considering the enriched case?
Yeah, so I've given this some thought. It should be possible, I think. Like I haven't really thought of any kind of any obvious objections to that. So that's something that I was thinking of doing at some point later. So yeah, like I think you should be able to take something like a single sorted or multi-sorted, like essentially algebraic theory or like a partial algebraic theory of some kind, and do a very similar kind of thing. So I don't see in principle yet any obstructions to doing that. So yeah.
Okay, great. Thank you very much.
Thank you.
Last chance for questions that are not me. Okay, then let's thank Jason again.
Thank you.